don't think he's gonna respond to you, Kamu. I hate to break it to you.
Nah, Pravir, no.
Okay, let's start. So Isaiah asked for chemical bonding. So when we work with, according to Sir, there's only three kinds. So there's covalent, molecular. So I'm just, which is between a non-metal and a non-metal. Right.
Put your volume down, hey boy. Put your volume down. I'm busy.
Come on, please go on mute. Turn your
Shut up,
camera
bro.
off.
My camera, I don't care as long as it goes on mute. Right. Then how it works is simple, right? Because what happens is um, so non-metals have a tendency to gain electrons easily, but if they both non-metals, you can't just say, oh, they're not going to give up their electrons. Now all forms of chemical bonding is based on the valence electrons, so you should always have a periodic table with you because we heavily rely on it now to so then let's look at an example. Let's say um, carbon bonds with hydrogen. Now, carbon has a valency, has four valence electrons, while hydrogen has one electron. Now, the thing with this is you always want to fill up so when you're working with non-metals, the all eight valency it must have eight valence electrons when it's done. So when in red, the those are your electrons that you get from hydrogen. But the problem is that it doesn't give it up simply. It just doesn't give up like that because hydrogen also wants carbon's electrons. So what you're gonna do is when you indicate this, you have to indicate an arrow going like this. Now, there's only one, this is only filling one spot. So we have to draw another hydrogen, and another hydrogen, and another hydrogen here. Because there's space for four electrons. So all of them are indicated with these two arrows here. These arrows here. So when it's done, what happens is carbon's gonna look like this here. Let me use so the X's that are in a different color, that's what it gained from the hydrogen, right? No, let me redraw this. Right. So now once you indicate that, let's say it asks you for Lewis diagram, but 90% of the time you end up with a Cooper diagram. So let's say the question asks for Lewis. What's gonna happen is you have hydrogen, 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 and carbon in the middle, where each hydrogen will share the shade of one bond. So here and here, then here and here, here and here, here and here. Now when we indicate this, let me try. You don't get it. Pick up pen. Thinner. Right. Now hydrogen now shares only one electron with carbon, and carbon gives hydrogen. Well, shares one with hydrogen. So when we're doing, so this is what your Lewis diagram should look like. But then for a Cooper, now let's say Sir doesn't specify what he wants. 90% of the time, you should do Lewis and Cooper, but Cooper will be your final answer. So Cooper indicates the bonds with a line. Now, here's how you know how many lines to draw. It's based on electrons because let's say I have two electrons. This is one pair. This is one pair. Therefore, one bond. If I was sharing four electrons in total, then it would be a double bond, which is two pairs, meaning two bonds. So in this case, hydrogen and carbon are sharing one bond with each other. So when we indicate this, it's going to look like this here. And now it's optional to draw the valence electrons, either way it's right. But yes. Okay, does everyone understand covalent molecular? Oh, okay. Let me just open this quickly.
Yo,
Yes,
yo, yo,
yes, yes.
yo.
Are you asking a question?
Yeah, I am.
Okay, what's your question?
I'm just checking, right? Covalent bonds is only with non-metals, right?
It's between two non-metals, as I've stated right here.
Okay, I'm just making sure, bro. Yeah,
Yeah, as it clearly fucking says on the page.
yeah, Isaiah, please.
Okay,
Oh, thank you.
yes. Right. Now, when we look at molecular, covalent molecular, there's something called polar and non-polar. This only applies to this kind of bond. So polar and non-polar. Right. So this also you have to heavily rely on your periodic table because you are not learning the electron negativity or affinity. Right. Now, what this means is if it's polar, because when they share electrons, it's not an equal share. One element will pull harder than the other one pulls. So, for example, hydrogen, if you look, it has 2, 1, while carbon has 2, 5, meaning carbon pulls slightly stronger. Now, how do we determine whether it's polar or non-polar? Right. It's polar when if you take the 2 and you subtract it like this, and you get this means it's polar. But if it was 0, that means it's non-polar. So if you look at it, just find the page. Right. Now if you look at two elements that aren't necessarily the same yet have the same. Yes, come.
Okay. So then, isn't it? We're talking about bonds here, right? So then, for I'm just trying to make sure I'm understanding what you're saying, right?
Yes.
So then, isn't it you have hydrogen and carbon there? You minus the what you call it? The what is those numbers at the top? The valence electrons, right?
No. In this case, it's the electron negativity
Oh,
or the electron affinity.
okay. So when you minus those, and then hey, move. You minus those, and then you get a value that's not zero. That means it's polar.
Mm. Yeah. So let's say the values give you 0, then it's non-polar. If they don't give you 0, then it's polar.
Oh, okay. Thank you.
Because non-polar is pure, is considered pure.
Oh, okay.
So like let's say you have here's an example here. Carbon, which is 2, 5, and sulfur, which is 2, 5. When you subtract them, you get 0. Therefore, it's non-polar.
Oh, okay.
So when you identify a bond, let me think of an example. Let's say you have H, hydrogen, and hydrogen bonds with oxygen to make, no, it's hydrogen bonds with oxygen to make water. This is water. Now, question is, how was this thing formed? So you would have to do it like this. Hydrogen has 1, hydrogen has 1. Oxygen, 6, 1, 2, and 6. Now, here's where the problem arises because this is H2O. That means that this is not balanced. So if we put a 2 here, that means we need 4. So you're going to have, do you guys understand how to balance equations? Yes, Kamo.
Now I'm saying I know how to balance the equation. So
Okay. Let me not use this example rather. This is not a very good example. Let me instead take one from the book. Yes. I don't understand anything. From where, Josh? Like anything, nothing. Okay, let me look at this one. Yeah. Pitch size. That's okay. Turn the periodic table. Let's say carbon. Let's start it simple. And carbon and oxygen make carbon dioxide. Right. Now, we know oxygen is diatomic in nature, carbon. So, carbon has 4 valence electrons, oxygen has 6. Okay, let me not write it there. Right. That means that 2 go here and the other 2 go here when they bond. So now we know that wait, we need 2 oxygen to form, and oxygen does occur as diatomic. So we know that the chemical formula is this to make carbon. When you burn carbon in oxygen, you do get carbon dioxide. But if we take this further from here, carbon, oxygen, oxygen, let me not put that so close. Okay, right. We know that it's going to look something like this here. Right. Now, going even further, this we can see it's only sharing 1, so it's just like this. The sulfur only makes, oh no, wait, sorry, not sulfur. It's supposed to be carbon. And it's, well, no, I drew this wrong. One, two, three, four. 1, 2, 3, 4. Right. And the reason why is because carbon will always make 4 bonds. So even if it's only bonding with one element, it will find a way. So it will look like this here. Double bond with carbon. That's Cooper notation. You don't, if you want, you can put this. But if they ask you to identify this, what you have to say is covalent molecular. And so it's a covalent molecular. Now, is it a polar or non-polar? Let's see. Carbon has 2.5 and oxygen has 3.5. So when you subtract this, you get a difference of 1 or 0. Therefore, it's polar. And that's, so if it asks you for the bond, this is what you do. If it asks you for a diagram, this is what you do. That's everything for this kind of bonding. Does everyone understand this? Yes, Cabo.
But I'm good, bro. I'm good.
Okay, put your hand down.
That's Kunashi. It's Kunashi, bro. That's Kunashi, I think.
Okay.
Hey, Kunash, speak
I
up, bro.
can make you lower your hand. I don't need.
I think mine's been up, bro. So I forgot to lower it. That's my bad.
Right. Okay, right. Then next we're gonna do ionic. Right. Ionic is between a non-metal and a metal. However, today we learned that let's say you get a semi-metal. Oh no, wait, sorry. That's not here. That's here. So I said non-metal. It's between a non-metal and a non-metal covalent molecular. However, there is an exception. If it's between a semi-metal and a non-metal, because then technically is a combination of a metal non, and this is just non. So it falls on the covalent side, right? But for ionic, um, for an ionic, it's just non-metal and metal. So how this works is metals easily lose electrons. Now, from everyone on this call, who can tell me why? There's a few reasons. Only one person. One, you can give one reason if you know. Do you guys seriously? Do you guys not? Yes.
Is it something to do with a sea of delocalized electrons?
Right. Reason number one: sea of delocalized electrons. Thank you, Zara. Right. So a sea of delocalized electrons has to do with metals. Now, the reason why they lose electrons so easily is because your their valence. So let's say this is the nucleus, and this is the valence, your valence electrons, right? Your valence electron is somewhere here and here. Let's say here, right? Now the problem is in metals, things overlap. The outermost shell and energy level overlaps. Now it becomes a problem because then electrons start jumping into the next one. And the reason why we use the word delocalized is because that atom, that electron no longer belongs to a specific atom. So if we look at this results in having something called positive kernels, excuse me, because they lost their electrons. So it's a positive atom kernel, and a C, and then negative, your electrons is just a sea of delocalized electrons. So because they don't, these electrons here, now these have bigger atomic radii, because as you go from right to left, the radius increases, and as you go, um, let me just make sure I'm saying the right thing. And as you go down, the size increases. So metals, because they're on the left, will tend to have a bigger atomic radii. Therefore, they overlap, and then the electrons become delocalized. Now, because now the electrons aren't inside the atom technically anymore, they can easily just go away. meaning metals easily give electrons. Right. That's that's basic. That sums up all three, everything you need to know about metals. Now, um, non-metals, because they have a larger atomic radii, they easily take electrons. They take the electrons. Meaning, if a metal, let's look at a chemical example. Let's say you have sodium and chlorine. Now, chlorine is diet. Have no fear, I scope here. Diatomic, right? Sodium not diatomic, it's a metal, right? So that gives a, now if we want to look at how they bond, how do they bond? Because Na is in group one, it can easily, it only has one valence electron. Chlorine, on the other hand, has seven valence electrons. Now, if you look at it like this, would you rather lose seven for chlorine, right? Are you going to lose all seven, or are you going to gain one? It's easier to gain one than lose seven. So that's how it happens. So now, when the Na gives it here, the Na gets a positive charge of +1, and the Cl, now, thing is, it's occurs diatomic, but we'll sort it out now, -1. Now, then you're going to write it like this, Na +1 in the big brackets, Cl with all your valence electrons, and the one that Na gave. And that's going to become, if now, -1. If you swap them, the charges, you get Na1 Cl1, which is NaCl. But when we balance this equation, NaCl, there's two chlorines here, and there's only one chlorine here. How do we fix that? All we have to do is, if we make two of it, now there's two chlorines, so the chlorines are balanced. But Na, the sodiums, only has one, so it makes like that. And that's how you would balance it. And that's actually a better way to remember how substances are formed, because you can see how many bonds can a specific element form in this case. So this is what a ionic bond looks like. The metal loses a certain amount of electrons. The non-metal takes those electrons. Then, because now they are now one's positive and one's negative, they are now attracted to each other. Yes,
Can you quickly please explain the delocalized thing one more time?
delocalized. Okay, right. So if let's start from the basic. Right. Let's say you have the nucleus of, let's say this is lithium, right? Obviously, I'm not going to write the protons and whatnot, because when we look at the atomic radii, right, it increases in size going from right to left and increases going downwards. This is the atomic radii. The bigger the atomic radii, the bigger the atom is going to be. So in this case, we have, let's say, lithium. Lithium has 3 protons, 4 neutrons, and it has 3 electrons. So 1, 2, and 3. Right. The problem is, because it has a much larger atomic radius, this electron is quite far out. This one here. This guy is quite far, meaning there's going to be less of a pull force, because the general charge of a nucleus is positive. That's why the electrons are attracted to it. Something called electrostatic forces, right? Now, because he's so far, this electron is so far away from the nucleus, it can easily just go out, go away. But because having such large atoms is not going to make the material dense, inside one, let's say a molecule of a let's say you have a pack of lithium in your battery, right? Your batteries are made of lithium, and you have another one here. The problem is that the outer energy level overlaps. So not only is this one weak, this one overlaps. So now it can easily jump between the two. And because now it's jumping from one atom to the next atom, it's no longer it's no longer belongs to an atom. Therefore, we say it's delocalized. Because if it belonged to an atom, it would be localized. Think of it like this, right? Your phone has a local storage and cloud storage. When you back it up, that cloud storage is now delocalized. It's no longer on your phone. But let's say you keep it on your phone, that's still localized. So that's how you should remember it. Because the cloud will always be delocalized. Because local, think your device itself. So now, because the atoms can easily jump and don't belong to a specific, the electrons can easily jump from one atom to another. That means that at some point, the atoms are going to have a positive charge. And there's just going to be electrons here floating around in a sea. That's why we call it a sea of delocalized electrons. Because they easily jump and then they overlap the outer shells, so they don't belong to a specific atom anymore. So they become like the sea. But they're still attracted to it, just by not that much. Do you understand it now?
Yeah, thanks. Appreciate it.
Okay, yes.
So can you please explain relative atomic mass?
Okay, I'm not done with the bond. Okay, well, so the last type of bond is metallic, but I think I went over this twice, the sea of delocalized electrons. So that in a metallic bond, let's say copper, this is all that happens here. You have a sea of delocalized electrons. That's why metals conduct heat easily and electricity easily, because energy easily passes through here because the electrons are just floating, basically. Right. You want a relative atomic mass. Yes.
So is my mic not is my mic working?
Yes, I can hear you. So you want relative atomic mass, right? You want me to teach
Yeah,
that?
yeah.
Okay. Uh, okay, here's the formula. Yeah. Right. Pick a random element from the periodic table, someone.
Copper.
You wanna do copper? Okay.
Right.
Right. So we're gonna do copper then. Let's do copper.
Right.
Right. Copper has 29 and 63,5. Right. So in its normal state, it's copper 64. The most common states will be copper 64. You do get copper 63 and copper 65. So this this is the isotope, right? These are the different isotopes of copper. And then the percentage abundance of them is, let's say this is 10%, this is 50%, and then this is 40%. Oh, well, no, let me not change this number. This is 9%. And then they say they don't give you this one, right? But we know that fine. Out of out of 100%, this has to be 49%. How do we calculate this? If you add these two up, you get 59%. and you need something out of 100%. So 100% minus 59% is 49%. Right. So now there's two of the same formulas. So relative atomic mass, or RAM, of copper is equal to, you say, so you take this number here, the isotope number, which is 63, times by 41. I'm going to show both versions of the formula. Plus 64 times 50. Plus, so you're always going to take the isotope number times by the percentage of abundance. Plus, and then you add them. 65 times 9. And then you just say all over 100. And then when you put this in your calculator, you will get an answer. Let me just find mine. Uh, 64 times 50. And you should so then when you get this, you're going to get 63,68 rounded is 64. And that's about right because we got 63,5, 63, if we round, it gives us 64. So the RAM, the relative atomic mass of copper, is 64 AMU, atomic mass units. You understand that now? Yes. Sorry.
Do we always round it up? Like
It will tell you how many. It should tell you how many. Yeah, because I'm looking at the past paper, round off to two decimal places, so 63,8, yeah. Okay, next.
Can you go over ionization energy?
Okay, now this one. Right. Thing with ionization energy is that all it has to do with is removing electrons. So if we wait, right. Give me two elements. Give me two non-metals.
Oxygen and fluorine.
Okay. Right. Oxygen and fluorine. Oxygen has 6. Oh no, I drew an extra. 6 valence electrons. Fluorine has 7. Right. I know you choose that for some reason, Kamo. I just can't prove it. Right. So if we look at it right now, that's the valence electrons. However, in total, oxygen has 8 and fluorine has 9. So now if I draw the diagram of oxygen, which is 8 protons, 8 neutrons, and then 8 electrons. So 2 here. Okay, obviously this isn't 100% accurate because these two will repel each other, but yes. Right, this is of oxygen. So for my first ionization energy, I'm going to be removing this one here. So when we write it out as with the notation, this is 1s2, 2, so yeah, 2s, 2 and 2s4, 6, 8, right. Now, that means,
2p4.
oh yeah, sorry, 2p4. Right. The most we will work with is possibly D, but I doubt it. Right. P4, yeah, that's 8. Right. So now when we remove it, we're removing this one from a stable shell, the stable orbital, because they spin in opposite directions, the electrons, meaning they keep it balanced. However, let's say I remove one. I'm gonna to remove it because they're in opposite spins. They obviously will attract each other almost. To remove it is going to be very difficult. So for the first ionization energy, it's going to be very difficult. So it's going to be difficult. But if we compare that to fluorine, for example, which is 1s2, 2s2, 2p5. Now, because the thing so all that's different is if I look at my oxygen model and we change there's another one here for fluorine. So now we're removing it from a single one. There's only one spinning, not two. So it's easier to remove it because that shell, this orbital here, is already unstable. Because, well, yeah, it's unstable because there's only one. Everywhere, so no, generally speaking, you want a full shell will be more difficult to remove it, even if it is slightly further. So now fluorine has a so if it asks you to order it in first ionizing energy, then you would say that oxygen is greater than fluorine. But for second, i.e., you would say that, okay, I've already removed this one. So now we're working with 2p4, meaning it's going to be difficult again. But here we're working with 2p3. So fluorine 2p4, but oxygen 2p3 because we already lost one. Therefore, fluorine requires more energy than oxygen. And energy decreases as we move down and decreases going, sorry, wait. Yeah, it decreases going down, but it increases going right. The reason it has to do with atomic radii, sorry. And the reason, and this side is only metals compared to non-metals. So there's a multitude of reasons for that. So when you look at it, get it into this notation here. Let me just find what it's called. Oh, oh no, this is an alpha. Wait, I write it down. Oh, this is called the electron configurations. So this one is just the normal way with the noble gas. You just write a noble gas in place of that, and whatever is missing, let's say you have a 2p5 missing, you write it there from the noble gas. That's known as noble gas notation.
Wait, can you explain the noble gas thing that
Okay,
you just did?
right. So let's look at oxygen. Oxygen is not a noble gas. We know this because it's not in group 18. Right. Now, the closest one is not neon because we're not going to gain. So we look at the one before oxygen, which is helium. So helium has 1s2. Oxygen has 1s2, 2s2, 2p4, excuse me. So now, if they want noble gas notation, this is helium. What you're going to do in brackets, helium. Meaning, we already took care of this part. What's left? This here. So then you write 2s2, 2p4. That's noble gas notation. Right. Then F-bow diagrams is simple. It's just this here, but we represent it with a block, a half arrow. This is F-bow. Then orbital is a circle with a full arrow. Now, you guys need to make sure you know your rules. Or else, yeah, I know. You need to know, like, for example, Pauli's exclusion principle and Hans rule, which is, let me find it. Pauli's exclusion principle states that only a single orbital holds a maximum of 2 electrons. Hans rule states that an electron is filled one at a time in an orbital before the second one is placed in. So let's say you only have 3 electrons in the 2p orbital, and you only have 3. You're going to fill them in like this. Oh, sorry, not full arrows. Like this, yeah. But then let's say instead, so you're going to do it like this, not, you don't put 2 and then leave the one block completely open like this. That's wrong. Okay, anything else? Yes. Yes. Kunashe.
Repeat the meta classification.
What?
Meta classification. Why is
Uh,
the mic so shit?
Did you possibly throw it in the deep fryer? Can you repeat that? Can you repeat that?
Actually, please get a better mic.
Classification.
Or to type it out. Try.
Where you, what do you mean by that? Where you talk about mixtures, compounds, elements, like that. Oh no. You tell me you don't know what's a compound, Kunashe. Okay, let me just. Yeah. Ooh, let's see how much time we have left. 15 minutes. Okay, so elements is one type of elements. It's a pure substance, cannot be broken down further. Let me just find it quickly. Right, it consists of the same type of atom. However, diatomic elements have 2 of the same atoms, however they bonded together. Right, now, how do you guys remember the 7 diatomic elements? Does anyone have a specific way? How do you remember the 7 diatomic elements?
Have no fear.
Have no
Ice
fear
cold
of
beer.
ice cold beer.
I said it first. I
Have
said it first. I said
no
it first.
fear
Exactly.
of
Pinky, I said it first.
ice
It's
cold
crazy.
beer.
Hey, I said
This
hey.
this
Hey,
fat
Right.
is crazy, bro. Look at
Hey,
I'm
hey,
fucking up
hey,
over
hey,
here.
hey, hey,
this
hey,
fish has lost his mind, bro.
hey.
Right. Hydrogen, nitrogen, fluorine, oxygen, iodine, it's called chlorine, and bromine. Right. Have no fear of ice cold beer is quite easy to remember. Hydrogen. Right. Now, that means that there's two of them just bonded together. Let me just see, is it considered a element or compound?
On my soul, it's considered an element.
According to?
According to who, big bro? According to me.
Alright,
On my soul, bro. On my soul.
the elements. Okay.
Yes. Get him, bro.
Right. Okay, right. That's elements. Anything you find on the periodic table is an element. Then compound. Simple, two or more elements. For example, carbon dioxide, water, glucose, etc., etc. Multiple kinds of elements, they bonded chemically. Mixture. Simple. You have, let's say you take carbon in the graphite form and you mix it with, let's say, you don't chemically bound, you physically mix it with, let's say, okay, no, that's a very bad example. Let's say you mix table salt with water, H2O. They're not physically bonded. They're not they're not bonded where okay, a bond forms between them because I can still separate it physically and not chemically. So let's say, for example, I burn carbon in oxygen to form carbon dioxide. This is a chemical bond. This is a chemical bond. They physically bonded together. This, on the other hand, is a physical mixture, or just a mixture. Right. Now, here's where it gets slightly more complicated. Well, quite a bit more complicated. Because, where's that? Right. Okay, so there's something we learned today. There we go. Okay. So, for example, carbon consists of a massive network structure that's bonded with carbon. So, if I take, for example, graphite, that graphite is bonded to each other like this, here, for example, and that's how it's formed. So these are repeating lattices. They covalently bond. For example, diamond, sulfur. So anything with the semi-metals and carbon will do that. So your semi-metals, silicon, AS, a few of we mainly look at silicon, right? So it's a large network of them. That's the only difference. Now, when we look at mixtures, there's two: homo, genus, and hetero. Hetero. Correct me if I've spelled it wrong. Let me just check. Yes. Oh, I'm missing an E. E-O-U-S. E-O-U-S. Okay, the difference is homo, you cannot see the difference. For example, your coffee. When you looking at your coffee, you've mixed your sugar and your water and the coffee beans and whatnot. You cannot physically distinguish the difference between each molecule anymore. You can't see the individual molecules, for example. However, with hetero, for example, if you look at, let's say a mixture of salts, let's say ice in a drink, you can still physically tell that there's ice cubes in the drink. So that's the only difference, whether you distinguish it physically or not. Okay. Any other questions? Kunashe, do you still have a question? I'm going to take that as a no. Okay. It seems like I've answered every question.
Pinky, do we need to know conversions and all that?
What do you mean conversions? From? Oh, you mean like those formulas?
Yeah.
Yes.
Oh no.
It's part of skills.
Oh no,
Like, for example,
didn't
what?
they say there's no skills in the test?
I don't know. I I don't know. I could be tripping, but
I mean,
like, if you look at it, it's not that bad.
Shoot yourself for a little shoot.
Okay, I'm gonna end it here then.
Wait. Let me just double check.
Are we serious, Cesare?
I'm still serious.
Use your mic.
You're the
oh, it's not. It's not. It's not.
Nice.
At least
What?
because Sir didn't say it when he was busy saying what's in our test.
Oh yeah, you're right.
Yeah, you're right.
Yo, how should you prepare for this test, Kabir?
Probably
Um,
who was the talking? Who was that?
is he serious?
Because I'm
No,
looking,
Tandarash, come on, bro. Mohammed,
There's a past paper
I'm looking at
that he
the
uploaded.
answers and I'm like, ah, I can't answer this. So
Mohammed.
You
No,
should probably Google it anyway.
Mohammed,
Wrong Indian surname.
Mohammed,
Nah,
please study.
now I've been
you're
studying the
full.
whole afternoon, bro. I'm so scared.
Oh, Mohammed, please remember. Mohammed, I beg you.
Nah, McHale is booked, fresh.
Okay.
That's insane. I won't lie.
No more.
That's like saying okay, let me not say it.